So let's start the session, the last session of Crypto 2025. Thanks all for joining. And yeah, the title of the session is Pseudorandom Functions. And the first talk will be about a fully adaptive threshold, partially oblivious pseudorandom function. And the talk is given by Ruben Becker.
So thanks for the introduction. This is joint work with Paul, Daniel, and Dominique. And when I came here, I was pretty good, prepared, and I had cool, colorful slides. But then my advisor stepped in, so I had to redo all my slides. So here we are. So what you will learn from this talk is that partially oblivious pseudorandom functions are just like really nice primitives. And we found a gap in a previous proof, but we also fixed it. So let's start. So the whole work around 2-hash Diffie-Hellman OPRS was started by Jarecki and Liu, and that sparked a whole lot of follow-up work. And this is just like new constructions. That is not even other papers that used it as a primitive that would never fit on a slide. But it also have applications, both in crypto. You can use it for password protected secret sharing, for password authenticated key exchange, private send intersection, and private information retrieval. But it is actually also deployed in the real world. So it is used in WhatsApps and Signal's end-to-end encrypted backup protocol, and also deployed in Cloudflare's privacy path. So what even is a partially oblivious pseudorandom function? I mean, we all know what a pseudorandom function is. It takes a key, an input, and returns a pseudorandom value. And an OPRF is simply a C-cube two-party computation to evaluate in PRF. So we have two parties. On the one side, we have the server who enters the key. And on the other side, we have the client who wants to evaluate the PRF on a certain input. And the server learns actually nothing from the whole computation. And the client learns a single PRF value per interaction with the server. So the difference to a partially oblivious pseudorandom function is that we introduce a public domain to the input. So now we have the input that says private, and additionally, part of the input is public, the domain. And that domain is explicitly leaked to the server. And now we want that the client learns a single PRF value per interaction with the server that is bound to that domain. Okay, now that we know what a PRF is, or what a partially oblivious pseudorandom function is, we want to instantiate it. And we're going to go step by step to the 2-hash Diffie-Hellman construction. We're going to start with a warm-up, just blind exponentiation. So the client gets an input, it raises it to a secret scalar. So it's blinded, sends it over to the server, who then raises it to K. And then the server sends it back, and the client can do deblinding by raising it to the multiplicative inverse of the blinding factor. We are just left with the input raised to K. So now the difference to the 2-hash Diffie-Hellman construction is just adding the 2-hash functions that are already in the name. And the first one is added by the client. So before raising it to the secret exponent, he uses a hash to group hash function and hashes that input before raising it to K. Then everything on the server side just stays as it. So you just still raises it to K. But then before returning the final value, the client hashes it once again together with the input. Okay, now we have an OPRF. Now we want the partially oblivious part. And we can actually leave the part about the private input just as before. We just have to somehow incorporate the public domain thing that we added. So what changes? First of all, the client sends the domain in plain to the server together with the blinded input. And then the server, before raising it to K, computes a bilinear pairing to combine the blinded value together with the public domain. And then everything else stays as is. So also the client does nothing else. And because of the linearity of the bilinear pairing, by combining the blinded private part of the input with the public domain, we get essentially a combination, like combined with the bilinear pairing of the private and the public part raised to R, so we can just still do the de-randomization just as before. Okay, so I hope I convinced you that partially oblivious pseudorandom functions are actually really nice. So now let's talk about the gap. And we're going to do it as before. We're going to do it gradually. So I'm going to talk you through the proof for the oblivious pseudorandom function, and then we will see how to extend that to the partially oblivious pseudorandom function. And we are doing a reduction to the one more gap Diffie-Hellman assumption. And that is simply, if you want to break the assumption, for example, a reduction, you take it takes the public key as an input, so just G raised to the private exponent K. It has access to a challenge oracle, and that simply returns group elements that serve as a challenge. And it also has access to an help oracle, which you can just give any group element, and you get back that group element raised to K. In the end, it has to output solutions, and solutions are of the form that you take a challenge and then raise that to K. And of course, we also want that it returns at least one more solution than the number of times it queries the help oracle, because otherwise it would be trivial to break. So now for the reduction, which is in the middle, it has to simulate the client and also to random oracles. And it has access to the assumption oracles on the right-hand side. So there is kind of a natural connection between the construction and the assumption. So if the client wants to hash an input or return a challenge element, we forward exponentiations to the help oracle, and then we can extract solutions from the final hash function. So now if the client wants to evaluate the PRF on a different input, we return another challenge element. And if the client is now somehow able to obtain a solution without interaction with the server, just in a magical way, then that is a break of the pseudo-randomness. But we can extract the second solution, and because we carried the help oracle just once, we also broke the assumption. Okay, so now we've seen how the proof works for the fully oblivious part. What do we need to do the proof for the partially oblivious part? So we definitely need another assumption, because the one more gap Diffie-Hellman assumption does not work well with bilinear pairings. So we need a natural extension to the bilinear setting. And that differs in comparison to the other one just by adding a challenge oracle, which returns challenge elements from the second base group. And solutions are now the form that we combine two challenge elements from each base group together and then raise it to K. So the proof now looks pretty straightforward, right? We just have an additional random oracle and we have an additional challenge oracle. So we just also for that random oracle return challenge elements. And that is actually how it was done in prior work. So now we return two challenge elements. We forward the exponentiation to the help oracle and can extract solutions. And if the client now evaluates the OPRF on a different input and somehow again magically obtains a solution without the interaction, that is a break. But we can also extract the second solution, and that is a break of the assumption because we only queried the help oracle once. But actually, there is a gap in this proof, because we have two different kinds of one more assumptions. So for the security definition of a partially oblivious pseudorandom function, as we said before, the client learns a single PRF value, which is bound to the domain. So what we actually have are multiple counters for the one more assumption, specifically one per domain. On the assumption side, we just say the reduction learns a single solution per head Oracle query. So we just have a single counter for head queries, no matter what you query the head Oracle on. And that gap actually leads to a problem. So if we go back to the reduction again, the server, the client does the random Oracle queries, and then the exponentiation, which the server just forwards to the head Oracle. And now the client changes his mind and says, okay, I'm totally gonna abort this protocol run. And instead, I'm gonna start a second one. And this time with a different domain. So we once again return a challenge element. He is now somehow magically able to obtain a solution without the interaction with the server. And that is a break. And we can actually extract the solution from the final hash function. So far, so good, right? We have a solution, so it should lead to a break. But actually, from the protocol run before, we called the head Oracle once, and we never obtained any solution for that. So that actually is not a break, because the head Oracle was queried once, and we only have one solution. Okay, so far, I always said that the client somehow magically obtains the solution. And in our paper, we were actually able to, this whole proof is done in UC. So we have an environment and a simulator to prove the security. And in our paper, we were able to construct an environment that simulates towards the simulation the one more bilinear gap Diffie-Hellman assumption, and then uses that simulator to break the actual assumption. And we have an explicit message flow that you can check out in our paper if you want. I don't have time to cover that in this talk. Okay, we have seen that there is a gap between the one more assumptions on the one side and the single one more assumption on the other side. So the question is, how can we fix it? And when we are looking back to the exact problem, then we see there is a temporal gap between querying the head Oracle and extracting solutions from the final Oracle. So what we could try to do, and we're heavily relying on the client to actually giving us the solution in the final hash function. What we can try to do is to extract the solution even earlier, because what the head Oracle returns already looks quite like a solution, right? The only problem is that there is an alpha in the bilinear pairing, and there has to be a challenge element. But we can do that with heavy solutions. We could let the client compute a non-interactive zero-knowledge proof. But the problem is that the relation involves the computation of a hash function. It is therefore computationally heavy, because we need a general purpose NISIC. And it is also a proof over the random Oracle, which is also not that nice. The other option is using the algebraic group model, which is a very strong assumption, and there are recent concerns about the soundness by Katz et al. So we try to avoid both. So looking back to the problem, there's also another option. Like the one option was to extract solutions earlier, and the other option is to avoid help Oracle calls altogether, which are unnecessary for the proof. And that is what we do with our new proof technique, which we call domain isolating Oracle programming. Because as we have seen, solutions from different domains cancel each other out. So even if you have one more solution for one domain, but you're missing a solution for another domain, then these just cancel each other out. So we need some sort of domain separation. So what we do is we guess the domain D star, where the break happens, and program the second random Oracle accordingly. And we can see what that means in the comparison to the proof as it was so far. There we just return challenge elements and use the head Oracle for exponentiations. And we're actually also returning challenge elements for the first random Oracle. But for the second one, we distinguish between the case that we have that special domain where the break happens and all other domains. And for that special domain, we actually continue just as before. We return challenge elements and use the help oracle for exponentiations. But for all other domains, we inject the trapdoor. So we return group elements that we know the discrete logarithm for. And now for the exponentiation, we can evaluate the bilinear pairing on the blinded input and the public key, which is like raising it to k, and then raising it to a to obtain the correct solution. We can also see how that works in the proof. So the first oracle run, or we guess that the break happens for d prime. Then the first oracle run, program run, we return a challenge element for the first random oracle, but for the second random oracle, we return a trapdoor. So for the exponentiation, we don't need the help oracle, but we can compute the exponentiation like directly with the trapdoor. So if the client now thinks he wants to abandon this protocol run, that is not a problem. And for the second protocol run, it actually uses that domain that we predicted the break will happen on. We return a challenge element, and now somehow is able to obtain that solution again. And that is a break of the assumption, because for that specific domain, it never queried the server. We can extract the solution, and now it is a break of the assumption because we never queried the help oracle. So coming back, you have learned that partially oblivious Pseudorandom functions are a really, really nice primitive. I really hope I can convince you. And we actually found a gap in previous work, but we fixed it. And we also had two additional contributions that I unfortunately cannot cover in detail in this talk. But we also found two other gaps in the previous ideal functionalities, which we closed. And we also solved a long-standing problem, which was repeatedly stated since 2020. And that is the combination of an oblivious pseudorandom function that is both supports proactive key refresh and is also fully adaptive secure. So thanks for your attention. And in case you are interested in password-based cryptography, we just recently had 2 papers accepted to AsiaCrypt. So you can check these out if you want on my website. So thanks.
Thank you for the talk. Are there any questions?
Yeah, no, actually not to the domain size, because we can say that we can use we just look how many times the second random oracle is queried. That is polynomial times because we have an PPT adversary. And then we can guess yeah, exactly. Yeah. So we don't have an exponential loss, but just a polynomial. Yeah.
Maybe a quick question from my side. Have you thought about constructions from other assumptions?
You mean like post-quantum, for example?
For example, yeah.
Yeah, not so far, but that is definitely like an ongoing research that would be interesting to see. Yeah.
Okay, thank you. So let's thank the speaker again. So the next talk will be adaptive security for constrained pseudorandom functions, and Kai Cheng will give the talk.
Hello, thanks for the intro. I'm going to talk about our paper on adaptive for the constraint PRF. How do I go? Okay. So in this paper, we consider a very special kind of PRF called constraint PRF. It was introduced in 2013 and has had a lot of applications. However, some applications require adaptivity that is beyond what is captured by the current thing. Therefore, we propose a fully adaptive definition. And then we also show that some natural constraint PRF indeed achieves our thing. But there's no free lunch, and our definition requires ideal models like the random oracle model. So a constraint PRF is a PRF where you can take the root key k that allows you to evaluate on the whole domain D. You constrain it on a set C to get a constraint key k sub C. The correctness says that the full key and the constraint key should evaluate to the same output for all x that is in this constraint set. And the security says that f of k of x should look random for all x that is not in C, even with knowledge of k sub C. The constraint PRF was introduced in 2013 by 3 different papers, and they go by the name of functional PRF and delegable PRF. It has many applications like the searchable symmetric encryption, I/O, punctual PRF, identity-based key exchange, and also the broadcast encryption. Okay, let's see a security game for the constraint PRF, where it has a initialization phase, a constraint oracle, and an eval oracle. The initialization and the eval oracle are similar to those of a normal game, while the constraint oracle will always output the correct constraint key given a set C that is chosen by the attacker. However, there is a trivial attack to this definition. The attacker can simply query eval on X, and then query constraint on a set C that contains X. It can then evaluate X using k sub C to check whether it equals to Y or not. And recall that the game will that in when B is 1, you will always return the honest output, but when B is 0, it's random. So then the attacker wins with non-negligible advantage. To fix this, early work placed different restrictions on the attacker. The non-adaptive definition requires the attacker to always query constraint first, and for later the eval queries, you can now query that on a constraint set. A more adaptive version kind of relax the first requirement, so that allows the attacker to interleave the constraint and the eval queries. However, we argue that even the adaptive definition, which we call partially adaptive, is still not enough for some applications in reduction proofs. Here, let's say the attacker is interacting with us that access to the constraint PRF. In the proof, we want to switch the output of the PRF to random, and then it's normal for the reduction to forward the queries to the constraint PRF game. Now, the reduction adversary has 2 options. It can either query constraint on a set C that contains this X to honestly give back the evaluation on X, or you can just query the eval query and get back a response that it does not know whether it's real or random. This boils down to the fact that the reduction adversary does not know whether later there will be a constraint query on the set C that contains X. For prior work, either avoided this analysis or use a hash function, we instead tackle the problem immediately and directly. So in this paper, we gave a fully adaptive definition. We then analyze natural CPF, like the hash CPF, the GGM, and AMAC. We then also analyze two applications. In this talk, I will focus on the definition and then use the definition to analyze the GGM construction. And then finally, I will talk about the SSE application. So our definition is analogous to the CMAC definition that was introduced by Joseph Yeager and Nervant Tiagi. Let's take CMAC as an example. Here, the attacker in the real world is interacting with an honest thing. And while in the simulated world, all responses to the evaluation queries are random. And then for exposure query, the simulator will be told the input and output pairs of all the queries. And then you will output the key that is consistent with this queries. This is impossible in the normal model. And therefore, we require a programmable ideal like the Rand Oracle model. Here, the P has two interfaces, lazy sampling and so the lazy sampling will taking X and simply return P of X. This later we are taking X and Y and sets P of X equal to Y. So now the simulator can simply program the thing so that the key that is returned is indeed consistent with all these queries. For compatibility, we also allow the attacker to query this program interface, and thus, therefore, the attacker can say he can internally simulate a programming thing so that he can do the reduction. Our definition, CMAC is similar. While in the ideal world, when X is never constrained, the evaluation query will simply return a random value. Otherwise, the simulator will be told the value of X and then return a value. For the constraint query, the simulator will be told input and output pairs that are inside this constraint set C, and also the constraint set C itself. It's worth noting that our definition places no restrictions on the attackers. It can make any queries it wants. Okay, so now I have talked about our definition. Now I want to analyze GGM using our thing. So let's consider. So GGM basically tells you how to construct the PRF from a less stable PRG, while the leaf nodes are the outputs of the PRF. And here we can view all the internal keys as constraint keys, and they allow you to evaluate on keys that are lower than you. The non-adaptive security was much easier, and but the partial adaptive security was only recently shown to be secure via a rewinding technique. For our stuff, we find it easier to actually work with a generalization called cascade, which will simply iterate the PRF on one input, and then on the intermediate keys are the constraint keys, and then the GGM is captured by viewing the PRG as a PRF whose domain is one single bit. Early work showed that the security of cascade directly followed from the security of the inner F. We similarly show that an F is in PRF implies that the cascade is a secure constraint PRF. So in terms of proof, we found it hard to prove the whole thing in one go. So we instead found that we can really draw the line anywhere to divide this constraint PRF into two small constraint PRFs. We can further and so really we are looking at a composed construction. And the proof goes where we simply switch once to simulated and then the second. So the catch is that here, for these in-between keys, there could be a race condition where you need to keep track of which simulator controls this key. Okay, so now this is probably the most important slide. So our proof works similar to the non-adaptive constraint PRF, and we have a similar bound. But this partial adaptive definition, which kind of sits in between our definition and the non-adaptive, it requires a harder proof and has a worse bound. So maybe the worse bound is due to limited proof technique, but rather than its true level of security. For our proof, our composition works nicely for non-adaptive constraint PRF and our CMACC PRF. However, we are unable to do a proof for this partial adaptive constraint the definition. Okay, so lastly, let's see one application called SSE. So in searchable symmetric encryption, there are two parties, the client and the server. The client has a key, and then the server has encrypted files. The client will send a query token that is encrypted, and then the server will make a response. Here, to facilitate search, the server will also keep the keyword to document the index table that is also encrypted. So what we consider is a scheme called Diana that was introduced by Boss et al. In 2017. So there are two types of queries, search and update, where update simply kind of links a document ID to a keyword, and then search will return all the document IDs that are linked to this keyword. What we want is that this update token to be random, even though the client has previously searched on a keyword that is the same keyword. And this is called forward secure. So for the actual scheme, here F is a constraint PRF, and H2 are hash functions. The client will generate a unique key W for each keyword W. You will then keep a counter to keep track of the number of document IDs that have been linked to this keyword. You will then use constraint PRF to evaluate the root key using this counter. The result is hash, and then the result is hash using another function to encrypt this document ID. To search, the client will generate a constraint key on a set that contains the current all the counters so far. The server can just then extract the document IDs using this constraint key. What we hope is that now, suppose the client want to insert a new document. This update token should look random, even though with knowledge of K sub C. Okay? In their work, they proved that these update tokens are random by viewing H1 and H2 are random functions that you can yeah. However, we ask the question that if these hash functions are necessary, because intuitively constrained PRF should already give you such a guarantee. But the catch is that their simulator run into a similar of a commitment case that we talked that we just talked. So the simulator in this time you need to generate query tokens, but it does not know what it contains. And during search, the simulator needs to generate a constraint key that is consistent with all these tokens. They can only do so in their work. They can only do so by viewing H1 and H2 are random oracle that you can program. However, for our definitions, we just have this guarantee. So the use of hash functions are unnecessary. Okay, so that's the end of my talk, and we have more stuff in the paper. Yeah. Thank you for your time, and I want to take questions if there's something.
Thank you. Are there any questions? So I'll start then. Can you go back to your slide with your main result before the applications?
It's a lot of clicking.
Sorry.
No, it's fine.
This one, yeah, this one. So for the second part, you say for the harder proof and the worst bound, do you see any? I guess, like, do you think do you have hope to improve this in the future, or do you see any barriers towards?
You just cannot, because there's this commitment problem that yeah, you have to use some kind of trick or magic, like you can when Oracle model. Yeah, so it's like we tried, but I mean.
Okay, so is there like a lower bound, or it's just like we would need really new technique?
So there is this upper bound. So, but it's like, yeah, like it's hard. Yeah.
Okay.
That's all I can say. Yeah, but maybe there are better things so we can do. I don't know.
Interesting. Thank you.
Mm-hmm.
Okay. So then let's thank Kai again. So the next talk will be succinct puncturable pseudorandom functions via memory tight reductions, and Patrick Harassa will give the talk.
Does this work? Okay. Thank you very much for the introduction, and thank you all for staying almost till the very end. So I'm going to be talking about a new type of PPRF called succinct puncturable pseudorandom function, or SPPRF for short, and about the applications it has when used together with I/O. Specifically, we're going to discuss how to discuss a succinct multi-party Nike, meaning a Nike that has no setup and where no message depends on the number of users. And as it turns out, this type of Nike then has applications, for example, in secure messaging. And this is joint work with Joel, Chris, Jerome, and Stefan, who's in the audience. So the starting point of this work actually lies somewhere entirely different, namely in the area of memory tightness, where one studies reductions for which the constructed adversary uses roughly as much space as the original adversary. There's a number of works who have re-examined some of the fundamental constructions in cryptography from this point of view. You can see a few of them on the slide. And we wanted to contribute to this line of work by examining a construction not studied so far, namely the GGM PRF. just as a quick reminder, the textbook reduction for GGM from PRG security is not memory tight, because to ensure a consistent simulation, the reduction needs to store a random value for every query prefixed by the adversary. And so the storage of the reduction grows with the query complexity of A, so it's not memory tight. And so the, at least for now, very theoretical question that I would like to start with is, can you give a simple black box but memory tight reduction for the GGM PRF from PRG security? And well, maybe the issue with the classical reduction already gives you a hint that this is going to be hard, because the problem is repeated queries by the adversary. So in a bit more detail, consider the following unbounded PRF adversary A that queries 1, 2, 3 up to Q, gets and stores all the replies, then makes the same queries again and checks for consistency, and then checks whether the replies it got are high or low entropy. Now remember that the PRF game here on the right is the combination between the PRG game and the reduction, but intuitively none of the two offers a lot of storage, because the PRG game gives you only one value and the reduction is memory tight by assumption. This means that if the combination of the PRG game and the reduction wants to answer the 2 rounds of queries consistently, it must necessarily give answers that are low entropy. But then we can efficiently simulate A by just letting it always say that the entropy is small. And if we now refactor, we have shown that the reduction together with this simulation technique efficiently breaks the PRG, contradicting the assumption. Okay, so there is no reduction of the time we're looking for general adversaries. The natural follow-up question is, well, what about adversaries that are guaranteed not to repeat queries? Can we give a memory type reduction for those? And it turns out that in this case, yes, we can. But the structure of the argument is quite different from the textbook proof. In particular, the top level hybrids are no longer level by level in the tree, but they're query by query. So this means that hybrid I answers the first I queries at random, which is fine because the adversary will never repeat queries. And so for consistency, like we don't need to keep track of what we answered earlier. While the other ones are answered as in the real construction. And to transition from HI to HI plus 1, we want to turn the answer to query I plus 1 from real to random. And let me show you how this works by means of an example. So just for concreteness, assume that we have a GGM construction of depth 3, and that the query was X star is 0, 0, 1. So the zeroth hybrid, the first one, answers as the real construction. And this hybrid has 2 functionally equivalent representations. One is the one that you see here with the root key hard-coded. The other one uses pre-computed PRG values and has the first layer of the tree hard-coded, and then looks at the first bit of the input and accordingly picks the subtree from where to continue the computation. Now in hybrid 1, we do our first game hop where we replace the 2 pseudo-random values up here with truly random values. Indistinguishability between the two holds by pseudo-randomness of the top right corner and by true randomness of the bottom left corner. And again, this program has 2 equivalent descriptions. One is the one that you saw earlier. The other one, well, you expand the second GGM layer and you hard-code that. And now you look at the first 2 bits of the query to answer the oracle reply. And from now on, we just reiterate the same changes. So from hybrid 1 to 2, we replace the 2 pseudo-random values with 2 freshly random values. And again, this program has 2 equivalent descriptions where we can expand the last GGM tree layer. And once we've made it to the bottom of the tree, we can fully randomize the last layer. And then switch to an equivalent program where the first thing we do is we check if the query was X star, in which case we return the purple value. This is the meaning of this box here. And once we did that, we can basically undo all the changes we did so far. So we move up the tree again, always keeping the reply at X star random. And this is how basically we randomize the reply to one more query. Now, if you watch closely, you will notice that so the storage of the reduction is independent of the number of queries of the adversary, but it is still quite large because it needs to store random values on the copath of the query. The question is, can we do better? And indeed, yes, we can. The key insight is that once we have replaced a value on the copath with a purely random value, this value is no longer involved in any further PRG proof steps. And so we can actually make it pseudorandom again and save on space. We do this by a construction that we call the storage gadget. This is essentially just an iterated PRG evaluation. What you do is, like, you pick a seed, and then you evaluate your PRG multiple rounds. And in every round, half of the output is a new value on the copath, and the other half gives you the seed for the next round. And on you go until you have expanded however many values you need. Using our storage gadget, the hybrids now look as follows. They're very similar to what we had earlier. It's just that in every round, we compute another value on the copath by the storage gadget. So the first hybrid is as before, nothing changes. For hybrid 1, we now sample a random seed for the storage gadget and hard code the first output of the gadget, this $2 value. And then when we move to the functional equivalent description and expand the GGM layer, we now also hard code the seed and let the program compute $2 on its own, $2 on its own. In the next hybrid, you will really see why this saves on space. So what we do next is we again sample a random seed, but now we use half of the output to compute a new value on the copath, and the other half to seed the storage gadget that we already have. And then again, when we expand, I forgot to say, indistinguishability here holds by, well, pseudo-randomness of this value and these two values here, and randomness of the others. And then when we expand again, we once more store the seed into the program, and then now let it compute both $1 and $2 on its own. And if you compare this to what we had earlier, like earlier here, we had two orange dollar values, but now we have only one. This is what allows us to save on space. And of course, this works for trees of arbitrary depth. So in the end, you need only $1 value for all the copath, for entire copath, instead of, well, n or lambda. And once we've made it to the bottom, again, we randomize the last layer. First thing, return the pink dollar, and then undo everything. OK, so let me back up for a second and take a look at what we did so far. So we have seen a sequence of hybrids that gives a memory type reduction for the GGM PRF for adversaries that do not repeat queries. And it does so by an alternating sequence of functional equivalence and computational indistinguishability steps that end up randomizing the output of the construction at one particular point. We call PRFs that have this property PPRFs with relaxed correctness, or RCPPRFs. So to reiterate, an RCPPRF is a PRF that allows transitioning from the real to the punctured program by a sequence of functional equivalence and indistinguishability steps. For now, this is just an abstraction of what we've seen in the example. And the proof that I've shown you shows that GGM is an RCPPRF. The name PPRF with relaxed correctness is, I guess, best explained by comparing RCPPRFs to regular PPRFs, where we have a punctured key that gives a functional equivalent description of the program on all inputs except one, where the output is randomized. So at a high level, what PPRFs achieve in a single step, in a single functional equivalence and indistinguishability steps, RCPPRFs spread out over potentially many more such steps. And relaxed correctness here means that the start and the end program here are not guaranteed to be functionally equivalent. And indeed, there isn't even a punctured key here in this formalism. All that we know is that there is this sequence of hybrids that allows you to do these game hops. And another interesting difference between the two notions is that while functional equivalence and pseudorandomness for PPRFs are defined somewhat separately, these are really like defined jointly in once for RCPPRFs. The reason why we believe that RCPPRFs are an interesting object of study is that they retain the usefulness of regular PPRFs when used together with I/O to build advanced cryptographic primitives. The techniques to do so goes back to the seminal work of Sahai and Waters, and roughly goes as follows. So suppose you're given an obfuscation M tilde of a wrapper program M around a PPRF with a hard-coded key K, and a challenge value Y star that is the output of F1 X star that you want to randomize in the process. Now you can do this as follows. So first thing, you replace F with the punctured program F star, which branches out at X star, and it returns Y star, and otherwise uses the punctured key. Then you can randomize Y reducing to PPRF security. And then finally, if your wrapper has the property that F star is never evaluated on X star in the execution, well, then by functional equivalence, you can just undo this and return back to regular F. So you have returned to the first coordinate while randomizing the second one, the challenge value. Now, the key insight here is that the same idea works also for RC PPRFs by simply slotting in all these hybrids that we have seen earlier in place of the one PPRF step. The big advantage of RC PPRFs over regular PPRFs is that punctured keys are usually large. So as far as I know, we are not aware of any PPRF constructions where punctured keys are small, let's say independent of the length of the punctured point. Take the GGM construction, for example, where you have a lambda bit value for every node in a copath. As a consequence, this results in large obfuscations because we need to pad the program to accommodate the proof technique, and so large public keys or parameters, whatever your application is. For RC PPRFs, on the other hand, there is hope that all these programs here can be kept small, which then would avoid you to have to pad, and thus would result in much smaller programs and much smaller obfuscation. We call RC PPRFs that have this property that all these programs are small, we call them succinct PPRFs. And we've already seen an example. So the GGM construction from earlier actually is a succinct PPRF because you have to store, like if you look through this, you have to store at most 4 random values. Yeah. So the big takeaway here is that when used together with I/O, SPPRFs retain the usefulness of regular PPRFs because the punctured program technique still works, albeit with some modifications here. But they get rid of the large punctured keys and therefore allow for a much more space-efficient primitive design. And in the last few minutes of this talk, I would like to give you an idea of how this works. So we construct a succinct multi-party Nike. The definition of the primitive goes as follows. So you have a bunch of parties. Everyone derives their own key pair. Then the public keys are exchanged or broadcast. And then every party separately again derives the shared secret key. Note that the succinctness requirement is already encoded in the definition. So for example, there is no setup here that depends on the number of users. There is no special party that sort of starts the protocol. The protocol is completely symmetric. Every party does its own thing, then the keys are exchanged, and then again, the shared key is derived. Correctness in this setting is the usual requirement that whatever secret key you use, you will up with the same shared key. And security means that if you know nothing other than the public key set, the shared key will look random. And our construction of a succinct multi-party Nike is heavily inspired by the work of Bonnet and Zandri. It goes as follows. So you sample a secret key, and then that's your secret key. The public key is a PRG evaluation of SK together with an obfuscation of this program that you see here. And to derive the shared secret key, you just evaluate one of the obfuscations sent around on your own secret key and the vector of public keys. Since in our construction, basically every party sends an obfuscation, the parties need to somehow agree on which one to use, and they can use the one with the lexicographically smallest first coordinate here. So this is sort of a tiebreaker mechanism. To prove security of this construction, we essentially follow the puncture programs technique. The proof has a few subtleties that I cannot go into detail here, but let me just mention them, and I'll encourage you to have a look at the paper. So our construction does not place an a priori bound on the number of users, which means that the SPPRF that we need needs to be able to process inputs of arbitrary length. This means that we cannot use the GGM construction that we saw earlier, because GGM is not even a PRF if you allow inputs to be of differing lengths. We solved this issue by introducing a ternary version of GGM based on a length tripling PRG. So the construction here is very similar to the ordinary, to the usual one. So to evaluate it, you just follow the edge path in the graph, but then instead of returning the target value, you return the middle child. And this avoids you leaking any of the values, and so you do not compromise pseudo-randomness of like related queries. With a proof very similar to the textbook proof, you can show that ternary GGM is a regular PRF. And we can also show that ternary GGM is an SPPRF. The proof is a bit more technical than the one we saw because it requires a more complicated storage gadget. More precisely, we use the binary SPPRF, so the regular one that we have seen earlier, as a storage gadget in the ternary version. The second wrinkle is that to achieve an input succinct construction, we use input succinct I/O for Turing machines. Prior work of Jain and Jin has constructed such an input succinct I/O from I/O for circuits, but using it requires giving proofs of functional equivalence in a special proof system, which has the disadvantage that it rules out the usual proof technique in I/O proofs that a random value lies outside the range of a length doubling PRG with overwhelming probability. We circumvent this problem by patching the programs technique, the puncture programs technique with range disjoint PRGs. This allows us to argue more or less along the same lines of the usual argument. Okay, so to wrap up, in this paper, we explore memory tight reductions for the GGM PRF. We show that they do not exist for general adversaries, but they do for adversaries that do not repeat queries. We observe that the reduction that we obtain naturally introduces the notions of RCPPRFs and SPPRFs, which maintain the advantages of regular PPRFs when used together with I/O while dispensing with the large program sizes, and then use SPPRFs and I/O to construct a succinct multi-party 9P. Yes, that's all I wanted to say. Thanks a lot for your attention.
Thank you. Are there any questions? Then maybe one quick question from my side. Out of curiosity, do you see any applications of your techniques beyond within I/O and memory tight reductions?
In the paper, we actually discuss an application of the succinct M-Nike to group messaging. So this is included in the paper. We are working on other applications of this. Let's hope I can tell you soon about it.
Okay, cool. So something to look forward to. Okay, then thank you again.
Thanks.
So the last talk of the session and of this conference, in fact, is traceable verifiable random functions, and Aditi Pratap will give the talk.
Yeah. Hi, everyone. Thank you for the introduction, and thank you for staying around for the last talk of the conference. So yeah, I'm Aditi, and today I'll be presenting our work on traceable verifiable random functions, and this is joint work with Dan Bonnet and Leah Rotem at Stanford University. So before I start with VRFs, I just want to briefly talk about accountability in general. So as we are all aware of, threshold cryptography has a wide set of applications because it allows us to distribute trust among multiple parties. So for example, you can take any secret and use T out of N secret sharing to split it among multiple parties. But the problem that we've been seeing is what happens if some of the parties start selling the shares that they have to an adversary. It turns out that in most existing threshold crypto primitives, there is nothing that deters parties from doing this. And that's where the idea of accountability comes in. What we would like is some mechanism to trace leaked information about the shares back to the parties who leaked this information. Note that we're not saying that we can prevent parties from leaking shares, but at least tracing can act as a deterrent because of the risk of being traced. So with that, there's actually been a lot of work in defining and constructing accountability for threshold primitives, starting with accountable threshold signatures, which were introduced originally in 2001, but there's been a lot of recent work in getting stronger security properties. More recently, there's also been work on defining and constructing accountable threshold decryption schemes and also accountable threshold secret sharing. And now we can move on to the topic of today's talk, which is accountability for threshold VRFs. So I'll start with a quick primer on threshold VRFs, and these are essentially a verifiable version of pseudorandom functions, which we've already seen. But for a quick primer, here we have 4 parties, and I'll always assume that the threshold T is equal to 3 for all the slides. So for a threshold VRF, we start with a function sampling algorithm, which will give you an evaluation key EK, which you can use to evaluate the function, plus a public verification key VK. Then we can use a key share gen algorithm to split this key among n parties. So now we have shares EK1 to EK4. Then if you want to evaluate this VRF at any input Z, you can send that to any 3 parties. Each of these parties can use their evaluation key share to get 1 share of the evaluation. So for example, party 1 runs the eval algorithm and gets Y1, which is 1 share of the evaluation, along with pi1, which is 1 share of the proof. We can then combine any 3 evaluation shares and proof shares together to get the full evaluation Y along with a proof pi. And the 2 key properties of a VRF are pseudorandomness. At a very high level, this means that the distribution of the output must be indistinguishable from random. And secondly, the evaluation proof must be publicly verifiable. So threshold VRFs have actually been implemented in practice in a lot of applications. The main ones include distributed randomness beacons and also deterministic wallets. And now coming on to the main motivation of the talk, which is traceability in VRFs. So as I briefly mentioned before, the scenario that we're worried about is what happens if some of the parties sell their key shares to an adversary. And here F denotes the number of parties who sell their information. So in such a scenario, what we want is if a whistleblower tells us that this was the information that was leaked to me, then we should have some way of tracing this back to the parties who leaked it. But in this simple example, where I'm assuming that the parties just leak their shares as is, tracing can actually be trivial. So for that, let's take an example of Shami secret sharing. Let's say we have a polynomial g of degree t minus 1, such that g of 0 is the evaluation key. Then we know that the evaluation key share of party 1 is the tuple 1 comma g of 1, and party 2 gets 2 comma g of 2, and so on. So this is just the usual Shami. But now the problem with this modeling is if somebody tells me that I got the information 1 comma g of 1 from some party, then we already know that party 1 must have leaked the share. But this example doesn't mean that we are done with traceability because these parties can do something smarter. So for example, they can cloak their evaluation key shares and make an evaluation box and sell that to the adversary. So you can think of this box as a stateless algorithm, which has the shares EK1 and EK2 embedded in it. And this box takes as input a value Z, the value at which you want to evaluate the VRF. And because it has 2 shares in the box, it will take 1 extra evaluation share as input. And with these inputs, it will give you the evaluation of VRF at Z, which is denoted by Y here. So this is a very general model of leakage, which captures essentially any type of information which parties might sell based on their shares. So with this model of leakage, now we say that if this box gets leaked, then a tracing party must be able to trace this box to all the parties which manufactured it. And this notion of traceability actually becomes important in all the applications of VRFs. So for example, in randomness beacons, the whole point of using a VRF is nobody can predict a future VRF value. But if some parties make an evaluation box from their shares, then they can already predict future VRF values, which is not ideal. So with this motivation in mind, in our work, we first define traceability for threshold VRFs, and we also give the first construction of this primitive, which is based on Parlier encryption. So let's start with the definitions. So I'll start with the syntax first. So we have the function sampling algorithm, which we also briefly saw before. For technical reasons, this algorithm also takes a number of parties and the threshold as input, and it then gives out the evaluation key EK, the verification key VK, and 2 extra outputs. So we have this thing rho, which we call the correlation string. So for today's talk, you can think of this as the polynomial G, which we use to generate the shares of all parties. So informally, this captures the correlation between all n secret shares. And then we also have TK0, which denotes 1 share of the tracing key, which will be useful for the tracer to trace evaluation boxes. Then we have the key share gen algorithm. This takes as input the evaluation key, the number of parties, the threshold, the correlation string rho. And the one main change that we make to the syntax is that the key share gen algorithm only outputs 1 share of the evaluation key. So here I'm getting EKI and a component of the tracing key as well, which is TKI. So if you want to get the secret shares of all n parties, you will essentially run the key share gen algorithm n times. Next, we have the eval algorithm. So any party I can use its evaluation key share EKI to get 1 share of the evaluation at any input Z. And we can also verify this share yi using the proof yi. And then we have the combine algorithm, which combines any t evaluations into a full evaluation and a proof. And then we can use the verify algorithm to check the evaluation. So far what we've seen is the usual syntax of threshold VRFs. And the new thing that we introduce is a trace algorithm, which takes as input the tracing key TK, and it gets black box access to this evaluation box, which was leaked by the parties. And it will give you a set J hat, which is the set of corrupt parties that we will blame for making this box. Just as a reminder, this evaluation box is some sort of information leaked by any F parties, which contains the shares of those F parties in it. And it takes as input a value Z and T minus F shares, and then it gives you the VRF evaluation. So with this syntax, let's now see what security properties we would want from such a primitive. So first, we have the 3 usual properties of a threshold VRF. Specifically, we have correctness, uniqueness, and pseudorandomness. So these are the usual notions, so I won't be talking much about these. But now the new security notions that we introduce are traceability. So at a very, very high level, this means that the trace algorithm should be able to trace this evaluation box to the F parties which manufactured it. Additionally, we have extra security properties to ensure that the tracer in our system doesn't get too much power. So specifically, we define tracer uniqueness, which means that even a malicious tracer with access to the tracing key should not be able to produce 2 valid evaluations for any given input. And lastly, we have tracer pseudorandomness, which means that even a malicious tracer shouldn't be able to distinguish the evaluation of the VRF at a new input from random, even if it can corrupt up to T minus 1 parties, and even if it can see arbitrary VRF evaluation. So for today's talk, I'll mostly be focusing on traceability, and you can find the other notions in our paper. So let's get a bit more intuition about the traceability notion before we see our construction. So at a very high level, what we want is that the trace algorithm should be able to trace this evaluation box to the F parties which manufactured it. So let's again see our example of 4 parties, where let's say the first 2 parties combine their keys and make this evaluation box E. In terms of notation, I will use J to denote the set of corrupt parties, which is 1, 2 in this scenario, and F denotes the number of corrupt parties. So given this box, we can run the trace algorithm using the tracing key TK, and let's say we get some set J hat. Now the goal of traceability in some more detail is if the evaluation box is good. So informally, this means that the box does actually give you the correct evaluation of the function with a high probability on random inputs. So it does work in some sense. So the goal is that if the box is good, meaning that it does work, then we should find all the F corrupt parties. So a bit more formally, this will mean that J hat does indeed contain all the parties in J. Moreover, we should never blame an honest party. So this means that J hat should never contain an honest party. So we use a game-based definition to formalize this, and you can find that in our paper. So with that, let's move on to the construction that we have in our work for a traceable threshold VRF. So let me start with a quick primer on Parlier encryption. So Parlier encryption was introduced by Parlier, and it has the 3 key properties which will be useful for us to build a traceable threshold VRF. The first one is it is additively homomorphic. And the second one is its ciphertext space is sampleable. So what I mean by that is if you look at Parlier, the ciphertext space is Zn square, where n is an RSM modulus p times q, where both p and q are safe primes. And by sampling, I mean that if you pick a random number and do modulo n square, you actually get a valid ciphertext in Parlier. And we'll see why this is useful for our construction later on. The last fact about Parlier which will be useful for us is that the number 1 plus n generates a subgroup with easy discrete log modulo n square. So this is all that we'll need to know about Parlier for today's talk. Okay, so let's start with seeing how we can build a VRF from Parlier, and then we'll see how we get our traceable threshold VRF construction. So this VRF was formalized in the eVRF paper by Bonet et al. In 2024, and this is how it works. So in function sampling, I just sample an RSM modulus n, which is p times q, and here both p and q are safe primes, so p is equal to 2p prime plus 1, and q is equal to 2q prime plus 1. The verification key for this VRF is just the number n, and the evaluation key is phi of n, which is 4 times p prime q prime. Next, to evaluate the VRF at any input z, the first thing we will do is we will hash the input into the ciphertext space Zn squared. And we can do this precisely because of the samplable ciphertext property. Once we get the ciphertext C, the VRF evaluation is simply the decryption of the ciphertext. So the evaluation is just the discrete log of c to the power phi of n. So this is the formal expression how you decrypt a Parlier ciphertext. So that's our VRF evaluation of any input z. For the evaluation proof for verifiability, we simply use a NIZK proof of discrete log equality. And it turns out because of additive homomorphism of Parlier, we can actually use simple sigma protocols in the group quadratic residue n square. So essentially, we just reduce the hash space to quadratic residue n square, and we can use sigma protocols. So for the rest of the talk, I will not be focusing on the evaluation proof, and you can find that more details in the paper. Okay, so now let's move on to our traceable threshold VRF construction, where essentially we will be thresholdizing the VRF that we saw in the last slide. So essentially, we are going to secret share the secret key, which was p prime q prime among the n parties. And here we make one more crucial change to Shamir. So we still have a polynomial g of degree t minus 1, so that g of 0 is the key p prime q prime. But for party 1, instead of giving it the evaluation of g at 1, which is the usual Shamir thing, we will actually sample a random number x1 from the space Zn, and we will give to party 1 the evaluation of g at x1. So the share ek1 for party 1 is x1 comma g of x1. Similarly, for party 2, we sample a random x2 and then give it g of x2 and so on. So this change, as we will see later, is actually very crucial in achieving traceability. So this is how we secret share the evaluation key p prime q prime among all parties. And one more thing to note here is that the tracing key tki will also contain the xi values. So for any party I, the xi will only be known to the tracer or to the party I itself, but nobody else would know this number. Lastly, to evaluate one evaluation share for our VRF, party I will simply hash the input z and raise it to the power g of xi. So if you've seen any like BLS or Parlier threshold decryption, this is essentially the same thing. So the evaluation share for party I will be the tuple of xi, which is its index, and hash of z to the power g of xi, which I will denote as yi hat. Lastly, if you want to combine NET evaluation shares, you'll essentially do Lagrange interpolation as we do in Shamir. So you just take the product of yi hat raised to the power of lambda xi, which is the Lagrange coefficient for party I. There are some subtleties here, but you can look at the paper for that. And eventually, we just return the discrete log of this number d. So this is how we thresholdize the VRF from Parlier that we saw in the last slide. So hopefully correctness is straightforward. We're just doing Lagrange interpolation in the exponent, so we get what we want. Uniqueness of this VRF follows from the fact that we are essentially decrypting a ciphertext, so it has to be unique by definition. And we prove the pseudorandomness of this threshold VRF based on semantic security of Parlier in our paper. And now let's move on to the last part of the talk, which is how can we achieve traceability for this construction. So for that, let's get a bit more intuition about exactly what the box does. So again, we have this example where let's say the first two parties combine their shares and make an evaluation box E. So as we saw before, this box takes as input a value Z along with one evaluation share. So I'm denoting that share here by a tuple x, comma hash of Z to the power G of x. So with these inputs, the box outputs some number y star. So now recall that I had this notion of a good box, which means that it should give you the correct output with some probability. So formally, what that means here is that the value y star must be equal to the discrete log of this large Lagrange interpolation with high probability. So I don't expect you to read this whole expression, but essentially all I'm saying here is that y star must actually be the correct evaluation with high probability. So for simplicity for now, let's assume that the box is perfect, meaning that it always gives me the correct value. So summarizing that here, so far what I've done is I've run the box once with these inputs and I've gotten some value y star. Now here's the key trick that we will use to trace. We will run the box again, but with slightly different inputs. So the second time I run the box, I'll use the same z as before. I'll use the same x as before, but now the evaluation share will be hash of z to the power g of x multiplied by 1 plus n. So now here we'll be using the fact that the discrete log is easy with respect to 1 plus n. So now let's say when I run the box with these inputs, I get some value y star 1. So in our paper, what we actually prove is that if the evaluation box is perfect, meaning that it always gives you the correct value, it turns out that the y star 1 minus y star, which is the difference of the two outputs from the box, is exactly equal to the Lagrange coefficient lambda x with respect to x, x1 and x2 modulo n. And this actually follows directly from the fact that the discrete log is easy for 1 plus n. So this is just the expansion of lambda x modulo n. So just summarizing that here, I've just taken the inverse because that's easier to denote. So far what we have done is we've run the box 2 times, and now what we got is y1 star minus y star inverse is equal to this expression x1 minus x times x2 minus x divided by x1 x2. So now this is the other observation that will allow us to trace. So let me define a polynomial h of y, which is equal to the product of xk minus y divided by xk for all corrupt parties k in J. So I'm defining this particular polynomial which has degree f, which is exactly the number of corrupt parties. Moreover, the roots of this polynomial correspond exactly to the xk values of the corrupt parties, just by definition. And now what we have here is by running the box twice, I have gotten one evaluation of this polynomial at the value x. So now we can use this observation to trace. So for the trace algorithm, recall that the tracing key contains all the xi values of all n parties. So what the tracer will do is as follows. It will get the evaluation of this polynomial h that we defined at f plus 1 different values of x. And it can do this by just running the box multiple times, and each time it runs it twice, as we saw in the last slide. So once the tracer gets f plus 1 evaluations, it can then simply interpolate this polynomial modulo n. So now we've gotten the polynomial h, which actually contains the xk values of the corrupt parties as roots. So now essentially all we need to check is for the roots of this polynomial. So for any party I in n, the tracer just checks if xi is the root of the polynomial h, then by definition it has to be a corrupt party. So we just add this party I in the set j hat. And in our paper we also prove that you'll never end up blaming an honest party here because the honest xi values are completely hidden from the adversary. So this is a very high level overview of how you can trace perfect evaluation boxes for a traceable threshold VRF. But what about imperfect boxes? So let me show you what the problem is, because I don't have time to show the solution. So this is a brief summary of what we ran the box with. So we run the box twice, and by taking this expression, we get one evaluation of the polynomial h. Well, now the problem is if the box is imperfect, it doesn't always give you the correct evaluation as output. So this means that the values y star or y1 star that we get from the box may not actually be correct, which means that the evaluation h of x that we get may not be correct. So now if we do interpolation over wrong evaluations, we lose all guarantees about who we end up blaming. So in our paper, we show that if we had list decoding algorithms over Zn, then we could have solved this problem. But turns out there is no known such algorithm. So because of this, we have to use some extra techniques to get around this problem. And you can look at our paper for that. To summarize, we give the first definitions of a traceable threshold VRF, and we also give the first construction for this primitive, and it's based on Parlier encryption, as we briefly saw. And one of the big open problems in this space is how can we do traceability when the number of corrupt parties is more than the threshold T. Yeah, thank you, and I can take questions.
Thanks for the talk.
Go ahead with your question. Thank you.
Thanks for the talk. I was just wondering if there is a real-world translation of the box, because if I would think of it, that would be like maybe in web page, they could submit like function shares.
Yeah.
But then if you submit, for example, for party 1 and 2, the
Yeah.
function shares, and 2 and 3, and then it's not working, then
Yeah.
it has to be the share of the third party that is embedded in the box, right?
Good. Okay, good. So in our paper, we actually show that you can do like a simple tracing, essentially like the way you said, but what we show is like there's some limitations with this. So the first is actually the tracer needs to know the shares of all parties, whereas in our scheme, the tracer actually doesn't know anything about the key itself. So like essentially for the trivial algorithm that you mentioned, we'll have to give tracer a lot of power. And the second thing that we observe is that this algorithm that you mentioned actually does not work if the box is imperfect. So we have like formal results in the paper. Yeah,
Okay,
nice
thanks.
observation.
Thank you. So in the interest of time, I think maybe we can take the other questions offline. Thank you very much again, and thanks to all the speakers of the session again.